Hello, everybody. We now move to the last section of Chapter 1, which is Section 1.5 on exponential and logarithmic functions. These are two types of transcendental functions. They play a key role in the study of calculus. You will realize as you study Calculus 1 and 2 how important that number is and why that number is such a natural choice for a natural logarithm. All right, so anyway, we have a wonderful topic to cover as we close Chapter 1. So let's get started in Section 1.5. All right, Section 1.5 is on exponential and logarithmic functions. The first one is about logarithm. I will start with exponential functions, and then we'll go into the second part of this chapter, which is logarithmic functions. I'm going to start from something very, very basic. I will talk about exponential, but that involves exponents. So let's talk about this simple function, 2 to the x, all right? And somewhere you learned that the exponent means the number of times you multiply the base number with, right? So 2 to the third, for instance, is what? It's 2 times 2 times 2, that's 8. 2 squared, I know this is very simple. It's 4. 2 to the first is 2 because it's 2 times, well, you just multiply 2 just once, and so you just have 2. And so what you have is the pattern that every time you go to the next one, 3, 2, 1, and so on, you're dividing the number by 2. And that's obvious because 2 to the third is 2 times 2 times 2, and 2 squared is 2 times 2, right? So you have one less occurrence of the number 2. And that pattern should explain why 2 to the 0th has to be defined as 1, right? Because you're dividing by 2. And you keep dividing by 2. So these numbers are decreasing from 3, 2, 1 to 0 and -1. And you can continue doing this to define what we mean by all integers as exponents. Okay, 2 to the third means 2 times 2 times 2. 2 to the negative first doesn't mean 2 multiplied -1 times because it just doesn't make sense. Okay, but by recognizing these patterns here, you will see that how to define negative exponents. All right, so this will be 1 over 2 to the nth power. That's how we define negative exponents. No problem, right? And 2 to the 0th is 1. In fact, any base other than 0 to the 0th power is 1. 10 to the 0th is 1. E to the 0th is 1. Okay, 0 to the 0th is another big issue. That's a problem. Okay, and that is not a defined number, and we'll deal with that when it comes to calculus 2, I think. Okay, so this is the idea, right? Now we have also, we can observe when you have 2 to the x times 2 to the y, see this first part is 2 multiplied x times together. The second part is 2 multiplied y times together. So if you multiply these, of course, it's x times and y times. You're just adding these two exponents. All right, so 2 to the third times 2 to the fourth is 2 to the seventh because you have 3 2's and 4 2's multiplied together. That's 7 2's, right? And similarly, if you divide 2 to the x by 2 to the y, then this is 2 to the x minus y. So the interesting and fascinating thing about exponential functions is that the addition can be performed by, multiplication can be performed by adding the exponents. Division can be performed by subtracting the exponents. And then one more, if you have 2 to the x raised to the y power, I mean, what is that 2 to the third raised to the fourth power? That's 2 to the third, 2 to the third, 2 to the third, 2 to the third, right? Altogether, you have 2 to the 3 plus 3 plus 3 plus 3, that's 12 part. And you can easily see that this can be written as the product of x and y. So when you take the x power followed by the y power, then the new exponent will simply be the multiplication, the product of x and y. Okay, and of course the number doesn't have to be 2, right? So these will lead you to the properties which we will hold tight. These properties will hold true for any kind of exponential base. For any base b, all right, so b is supposed to be greater than 0, because if b is negative, you'll have all kinds of problems in trying to define exponential function for all real numbers. And also, b should not be 1. You know why that is? If the base number is 1, this whole thing is kind of meaningless, because 1 raised to any power is just simply 1, right? So we usually avoid 1 as the base, even though you can talk about 1 to the 15th power or 1 to the negative 13th power or whatever. But for function analysis or analysis of these functions, we avoid using 1 as the base of exponential functions. All right, so for any base, we have these properties. These are called exponential laws, or laws of exponential functions. B to the x times b to the y is b to the x plus y. B to the x divided by b to the y is b to the x minus y. We don't have to worry about the 0 denominator here, because b to the y is never 0. Okay, and then b to the x raised to the y is b to the xy. All right, so these are the 3 properties of logarithm. No problem here. Okay, so what does the graph look like? Well, I don't know if you know this, but exponential functions grow exponentially. You say, duh, of course, that's what we mean by exponential. Right? But the word, when something is said to be growing exponentially, they use that term because exponential functions from mathematics, we know that they grow really, really fast. Okay, so for instance, 2 to the 10th is already over 1,000. Okay, anybody know what 2 to the 20th is? You can easily do this by calculator, right? It's going to be over 1 million, just about 1.04 million. By the way, this is an interesting question. If you think of applications, let's say you have a dollar bill. Okay, a dollar bill, that is the magic dollar bill. It reproduces itself every night. Okay, so on first day or day 0, you find a dollar bill, and it turns out on day 1 you have $2 bills, and on day 2 you have $4 bills, and on day 3 you have $8 bills, and so on. On day 10, you are going to have $1,000. Great, you can go buy a few things that you are interested in. But if you wait for another 10 days, on the day 20, you'll have $1.04 million. If you wait for 30 days, 2 to the 30th is going to be about 1 billion, right? It's an incredible thing. And so if you wait for 3 more days, 2 to the 33rd is 8.59 billion. Guess what? That's more than the population of the world. Here's another thing I often mention in other classes. Let's say you today become a guru and you start your own religion of one person. You're the only person that belongs to this sect or your denomination, whatever. Okay, and every year, the following year, you find another person, a friend of yours, that joins your club or your religion or your sect. Now you have 2 people in the whole world that belongs to your sect or religious group. Okay, and then the following year, each of you reaches to another person, so it doubles. 2 becomes 4, and in the 3rd year, it's going to be 8 of you who are in the sect, right? And the question is, how many believers do you have if no one dies? How many believers are you going to have in your organization in 10 years? And the answer is 2 to the 10th, which is 1,000 people. Now that's not big growth, right? I mean, after 10 years, you have 1,000 believers who may donate to your cause or whatever. So this is very slowly or appearing to be slow growth. However, if this doubling continues every year, it only doubles, right? It's the same number of people added every year. this math is showing us that in 20 years, you'll have 1 million believers, and in 30 years, you'll have 1 billion. And in 33 years, if the number of if your membership doubles every year, in 33 short years, less than half a century, you're going to conquer the whole world, because this is more than the number of people who live in our world today. So that is exponential growth, right? Doubling, of course, can't continue forever, because eventually something will happen. But mathematically, it is possible to see such fast growth, and all it takes is an exponential function with a number b that's greater than 1. Okay. This property here also gives us something. What is 2 to the 1/2 power? Okay, now you already know this because somebody taught you that this is the square root of 2, right? But if you have to define this on your own, let's say somebody gives you the responsibility of defining this so that all your future generations can benefit from this. And it has to be consistent to something you already know, right? We don't know what that is. Okay, but you can use this property number 3 to help you define this. Okay, after all, it is this number whose square is, and what is the property saying here? This should be the same as 2 raised to the product of 1/2 and 2, and of course that's 2 to the first, that's 2, right? In other words, the thing that you're trying to define is a number whose square is 2. Well, you only know one positive number that fits that description, and that is the square root of 2. Okay, so that's how you can define a rational exponent. All right, so b to the 1/nth power is the nth root of b, and b to the m/nth root is nth root of b raised to the mth power. All right, so this is how you can define now for all rational x. Okay. B to the x is well defined. Now, the rational numbers are dense, meaning that in any small interval, you can have rational numbers. And so now we have the definitions for negative numbers, negative, positive integers, and rational numbers. And if you are to define these, okay, so this is 2 to the x. Let's try to write this 2 to the x. It starts with 0, 1, because 2 to the 0th is 1, 2 to the 1 is 2, 2 to the squared is 4, and 2 to the third is 8. It'll be over here. All right, so the graph is going to go fairly quickly up higher like this. Right, and now if you go back the other way, 2 to the negative 1 is 1/2, 2 to the negative 2 is 1/4. It'll get really, really close to 0, but never actually touches the x-axis, right? So this is the function. Oh, by the way, I have filled all the irrational points by continuity. Right? We just assume that you can define this, continuously. So that is the exponential function. All right. So what do you know about the exponential function? This function f of x is equal to the b to the x, where b is greater than 1. It is always increasing. The domain, what's the domain of the exponential function? All of the reals. Okay, and it always goes through the same point. That is 0, 1. Okay, so the y-intercept is always going to be 1 for these functions, always increasing on negative infinity to positive infinity. All right, it gets close to 0 as x goes to negative infinity. And f of x is always positive for all x. So those are some of the properties of exponential functions where the base number is greater than 1. And by the way, if b is less than 1, okay, what you'd have is the opposite of this. Basically, like if b is 1/2, then 1/2 can be written as 2 to the negative 1. So 1/2 to the x is going to be that, which is 2 to the negative x. So it just becomes the opposite of this, and so that's what's going to happen. It'll be decreasing everywhere, but the domain is the same. It still goes through 0, 1, and instead of it getting closer and closer to 0 as x approaches negative infinity, here this happens when x approaches positive infinity. Regardless of the value of b, right? The exponential value, the function value of the exponential functions will always be positive and not be 0. Okay, so 2 to the x, 10 to the x, these are rather popular things, because we use base 10, and 2 to the x it represents a doubling phenomenon. So these are often used, but there's one important number, and in my mind, it is the most important number. And I am not kidding when I say this. I have come to the conclusion that the number I am going to introduce to you right now, which you may be familiar with already, is the most important of all real numbers, right? And that is this expression taken to the extreme. So here's a number, 1 plus 1 over n, divided to the raised to the power of n, right? So for instance, you can calculate this when n is equal to 10, it'll be 1.1 raised to the 10th power, right? When n is equal to 100, it's going to be 1.01 raised to the 100th power. And when n is equal to 1,000, then it'll be 1.001 raised to the 1,000th power. Okay, and in fact, you can take your calculator, as I'm going to do right now, and you can calculate these. All right, so what's 1.1 raised to the 10th power? And this is 2.593 and so on. Okay, now 1.01 raised to the 100th power is 2.7048. Now, why would anybody do something like this? Well, there is a reason, and it's actually was motivated by, of all things, financial calculations. And so it looks like, and people have discovered this, and by the way, the original motivation is what happens if the money compounds not annually, monthly, or even hourly, but every single moment. Okay, can you continuously compound and calculate compound interest? And the answer is yes, because this seems to approach a particular number, right? So what happens is, as people discovered, as n approaches infinity, let me just go ahead and erase these other things, okay? As n approaches infinity, this thing settles somewhere close to 2.71 by the way, there's a mnemonic device I'm using. This is, sorry, in Japanese. But if I just say a certain phrase in Japanese, I can keep writing this. It's ni te nai yatsu hai ya ni hashi go kure yo kono ni san. That's all I remember from my from on top of my head, but that's pretty good. All right, this number is defined as E. Now, what is E? Well, E is the limit of 1 plus 1 over n raised to the nth power as n approaches infinity. Okay, how do you know this number exists? Well, that's the history. You can read about this number. In fact, there's a book written about this one particular number. It's called The Story of a Number, and that number is a lowercase e, right? And consequently, the name of the book is E, but it's lowercase e. And so we have to make sure that you look up the name that is a lowercase. But anyway, you can read that book if you like. It's a great book. I highly recommend it. and I think it's a great book written on this one number. This number is so important that people can write a book about this and read about this. Why is this so important? Well, I hope in the next semester or two, as you learn calculus, you will appreciate this number as much as I do. And you will see how important this number is in all of mathematics. And in fact, as I studied more mathematics, past undergraduate into graduate level courses, this number keeps popping up. And you realize that this number is very, very special. And in fact, well, I may not want to talk about this, but we talked about sine, cosine, tangent, inverse functions, the cosecant and cotangent. And then there's a hyperbolic version of those: hyperbolic sine, hyperbolic cosine, hyperbolic tangent. All of those can be defined using this one number E, right? Which pops up in many, many different applications, like in the description of a normal bell-shaped curve and many exponential models. Okay, so E is, let's just say it is a natural choice for the base for the exponential function. So when the function is e to the x, often people call it the exponential function. So when you hear the exponential function, and when the speaker or the writer is a mathematician or scientist, probably they are talking about the exponential function with a number e as the base. Okay, it's a strange base to use. It's irrational. Okay, it's not even a fraction or a nice number, but it turns out to be the most natural choice to use as the base of an exponential function, and as you see later in the logarithm. Okay, so what is logarithm? All right, so we will pause this for a moment. And in the second part of section 1.5, I'll talk about the logarithmic functions. Okay, so let's stop for now, and then we will go into the next clip as we go into move from the exponential to log functions.